Hello, you're listening to Angel Nears, the podcast. Angel Nears is a Silicon Valley community for startup builders where founders and operators share their firsthand knowledge on how to build and scale startups. I'm your host, Oleg Kuchikov, and our guest today is Ryan Benmalek, co-founder and CEO of Daimon Labs, a developer of a language model software designed to provide human-like empathy and companionship. We're excited to bring Ryan on to talk about the rise of emotional AI and how machines are learning to understand and respond to human emotions. But before we get into that and the topics, Ryan, welcome to our show.
Thanks for having me, Oleg. Really excited.
Yep, we're excited to talk. Let's just get started. Where are you at and how's the weather today?
I am in Lower East Side, Manhattan, New York City, and the weather sucks. It's been gray and rainy, that very kind of I want to stay in bed and sleep all day kind of weather.
Right. Well, we call that podcasting weather over here. Let's get going. Just an intro question about you. How did you become interested in technology and research in the first place?
Yeah, so it's been a long road. I've been honestly obsessed with AI since I was a kid, and I read my first Isaac Asimov book in second grade. Lots of sci-fi, lots of that. Reading books about brains and consciousness and how are we put together, what are the elements, trying to understand it. And when I was 14, I got the chance to enter college early. And my decision process was super simple. It was, okay, well, they're good at computer science, they're good at neuroscience, I guess I'm going there. Did both of those majors, lots of research all the way from like sticking electrodes into neurons in the wet lab, predicting seizures, generating short stories with RNNs. This was pre-transformers, boosting convolutional networks for classification. And in my free time, I made indie games. So I guess that was the more sort of entrepreneurial product builder side of it. Then ended up going to grad school just to, learn more, build up my trade, really gain a deeper understanding of AI. Had a lot of sort of startup side hustles while in grad school. One sort of data labeling, data management thing. Worked on a self-driving race car company as well, and worked at a bunch of big research labs over those years too. And sort of found that, I really loved research. I really loved digging in, reading papers, running experiments. But there was something about the startup environment that, working in a team focused on the user and focused on actually putting out a product as opposed to just doing research in thin air, that I was a lot more amenable to. So that's sort of been the history over the past 10, 15 years.
It's really cool. And it sounds like you've had so many experiences. I understand you went to Cornell to earn your PhD in, I believe, their computer vision lab. Can you talk about what you did there? Like, let's narrow this down a little bit. What kind of projects were you working on when you were earning your PhD?
Yeah, so within computer science, I was focused on AI, specifically computer vision and natural language processing. Computer vision being sort of all the AI that has to do with visual input, with understanding what's going on in an image, generating an image, understanding video, and natural language processing being AI applied to text, so sentences, dialogue, generating stories, for example. I was very lucky to be co-advised. I had one professor working in computer vision, Serge Boulanger, and one professor working in natural language processing, Claire Cardi, and they sort of gave me the rope to hang myself with and study whatever I wanted to study. So I was all over the place in my PhD. I worked on self-supervised learning. How do we train neural networks to build representations of the world, to understand things without explicitly giving them labels? I worked on image generation in a conversational setup. I worked on novel architectures for natural language processing in sort of encoder-decoder situations, like for generating questions from graphs. I worked on reinforcement learning for learning representations. And honestly, I think there's a few other things in there that I don't remember, but all over the place, yeah.
That's wild. And like, give us a sense for like what this field was like at the time. Like, it's 2023 as we record this today. Generative AI and AI just in general is part of public knowledge. But when you were working on these things, what was that like?
Yeah, the biggest thing, honestly, when I first started back in undergrad was that nothing really worked and everything was really hard. Compared to now, where things have gotten a lot better, both in computer vision and in NLP. In 2012, neural networks had started to emerge and started to be, I think, more respected within the broader academic community of AI for solving these sorts of problems. In 2015, ResNets came out, and that was another mini revolution, particularly in computer vision. And then eventually it really came for NLP. So that whole experience, honestly, has just been year after year watching these models get better at these tasks, watching these systems get massively better, and then looking back 5 years and going, whoa, that's been an insane rate of progress. And look at all the things that are starting to be possible that just weren't possible 5 years ago.
You talked a little bit about an image project. I believe that was the Neural Painter project. When did you work on that? And what? We'll talk about it. Yeah, talk about the project first.
Yeah, so that was my very first paper. And really, the paper was a mix of a computer vision paper and an HCI, like a human computer interaction type paper. So at the time, this is pre-diffusion, GANs were all the rage. GANs being a generative adversarial network. So let's say I want to train a neural net to generate a picture, something that's in the continuous space. I'm going to train two models at the same time. I'm going to train a generator who's trying to generate pictures, and I'm going to train a discriminator that's trying to tell me when I give it a picture, whether that picture is real, taken from the data set, or fake, generated by the model. And you train these two models in concert together, sort of hoping that they'll bootstrap each other up, and you'll get a really good generator and a really good discriminator at the end. And GAN started with unconditional generation. So unconditional generation being, here's a bunch of images of whatever. It could be, written digits in MNIST, it could be frogs. And then getting a model where you can ask, hey, generate me an image from the distribution of data I trained you on. So generate me an image of a handwritten digit. Then people started doing class conditional GANs. So take a data set like ImageNet, where you've got 1,000 different classes for each, spread out over about 1,000 images per class. Say I've got 1,000 images of coffee cups, or I've got 1,000 images of frogs or of dogs. And class conditional generation was the ability to tell the generative model, give me a picture of a dog or give me a picture of a frog, as opposed to just give me a picture from the distribution you were trained on. And then people started using caption data sets. So these are data sets of images and captions, like a short piece of text describing them, and trying to invert it. So training a model that would take a caption and give you an image, which is broadly similar to a lot of the image generation stuff you see today. Think, Midjourney or Stable Diffusion. And when you look at this evolution, it goes from a user perspective, having difficulty specifying what you want the machine to produce, to having more and more control over that. And so what we proposed in that paper was the next step, we thought, which was a conversational system. So instead of a one-shot system where you put in a piece of text and you get back an image, we wanted the ability to chat back and forth with the computer to generate images. So you might say, please draw me a hummingbird, and get a picture back, and then say, actually, could you make the beak red? Get another picture back. And then one more edit, could you add some tufts to the head? And hope that in the next step, that edit has been done to the image. There were a lot of problems with getting it to work, but the biggest problem we ran into was data. And the reason was, at the time, there were no data sets for this task. There were no data sets out there that had the structure of, here is a command, here's the image that popped out, here's what I said to update it, and here's what the new image looked like. All we had were sort of images with maybe paragraph descriptions, or images with maybe attribute value descriptions, like a picture of a bird and then saying, red beak, tufted hair, blue belly. And so the big innovation in that paper was to say, how can we use these sort of paragraph level descriptive data sets, or these attribute value data sets, and sort of fake as though we had this conversational data set? And it turns out that if your description is structured in this sort of multi-step way, like I have a paragraph description with multiple sentences that focus on different pieces, or I have these attribute values, then you can just pretend that you have the data and sort of randomly sample where you're providing the image as supervision. So in one training step, you might say, okay, after the first 2 sentences, you want to generate this image. And in another training step, you might say, after the first 4 sentences, you want to generate this image. And we were able to mathematically prove that that was equivalent to actually having that data set at hand. So that was pretty cool. We got it to work. It does not look anything nearly as good as the image generation systems today. I think that's 5 or 6 years of more compute, more data, better algorithms. But it's pretty cool to see. I think maybe a week ago, OpenAI announced that DALL-E 3 is coming out, and they have this sort of conversational back and forth way to generate images. So that feels pretty fantastic.
Could you go back? Have you thought about like going back and maybe you say these things work in concert together? It sounds like on this Neural Painter project there was a lot of moving pieces. Have you thought about kind of like going back and replacing some of the parts with the better tools today, or is that just like a waste of time?
It would be a fun project to go back and say, okay, we don't need a GAN because now we have diffusion. So like you said, we had these 2 moving pieces that were really complicated to train together. Now we only have 1 piece that we need to train. Okay, we have language models which broadly understand language. We can start from pre-trained initialization. There's like maybe 10 or 20 things we could do to go back and improve it. But, at this point, it's sort of out there already. People are building these kinds of systems. And so I don't really feel the need to sort of revisit it. It's always more fun to work on something new.
And what was your biggest lesson that you took away from that project?
There's a few. I think one big one was the value of persistence, which sounds very cliche. But, in research, you'll often find that you have an idea and you want to make it work. And in order to make it work, you need to find 50 ways that don't work first. And so you need this strange sort of balance between having faith in the idea and being willing to sort of bang your head against the wall for months straight. And also the ability to say, hey, this isn't working. Let me move on to something new, which is not something I'm sure I've completely mastered yet. But that would be one big lesson. And then I think the other big lesson would be patience. This was a paper we were really, really excited about at the time, but we had the hardest time getting it accepted to conferences. I think we submitted it maybe 3 or 4 times in a row. And each time we would get the worst reviews. Like you'd get back 3 reviews and 2 of them would say strong reject and 1 of them would say weak reject. And I'd get demotivated. And my advisor, Serge, human angel that he is, would say things like, well, if you're getting reviews like that, you're doing something right. And at the time, I sort of waved it off. I'm like, yeah, no, you're just trying to make me feel better. But looking back, it was true. Maybe the idea was a bit too early. But, like I said, with DALL-E 3, you can see that out in the world today, and it's sort of starting to enter a lot of people's lives. So sometimes for an idea, you might need 5 years of patience before it sort of bears fruit.
Yeah, especially these like revelatory ideas or these things that are going to change things in a big way.
Totally.
All right. Well, this conversation's been incredible already. I kind of want to go back. We've been using a couple of terms that I just want to define before we really get into the main topic of our conversation today, which is emotional AI. Let's start with AI. We've mentioned it a bunch of times. Give me just a few sentences that describe what artificial intelligence is.
One thing that's really interesting in the history of artificial intelligence is that it seems to be the case that once a task is solved by a computer, we don't call it artificial intelligence anymore. Like spell check used to be artificial intelligence. Now it's just spell check, right? We sort of expect it to work. So there is this odd way in which AI is sort of what's at the frontier. A large part of AI nowadays is machine learning. So the standard way of programming is to say, okay, I've got maybe some inputs or some outputs. I know what my system wants to do, and I'm going to write an algorithm to transform these inputs into outputs. And a great analogy I always liked from a professor I worked with in undergrad, Ali Farhadi, was that what we do in machine learning is we write programs that create programs. So instead of writing 2 million lines of code for identifying tennis balls and images, we say, hey, we're going to go out and we're going to get this data set of pictures and boxes for where the tennis balls are. And we're going to write a program that takes in that data and generates a program for me that can do that task, which is a neural network. So that's machine learning. That's sort of the bread and butter of a lot of AI nowadays. I think if we want a really sort of high level definition, artificial intelligence in the limit is about creating machines that we can recognize as intelligent, because there's no, ruler out there for measuring intelligence, right? It's not like length or width or temperature. There's no quantity to it. Is a dog intelligent? Is a pig intelligent? We define it relative to us. So it would be something that we recognize as intelligent. It can use language, it can draw, and is adaptable over time. It has the ability to sort of change and adapt to the world. And I think the third sub definition I'd stick in there would be that it is agentic. It has goals and values and sort of pursues them in the world. But that's my definition, and you might hear different ones from different people.
For people who aren't familiar, can you explain what computer vision is and maybe some examples of how it's being used already today?
Sure. So computer vision is AI applied to a specific modality, visual input. So images, videos, maybe radar and LiDAR scans, anything that has to do with visually understanding the world. You see it everywhere nowadays. I think, everybody remembers old CAPTCHAs, the ones where it was 2 words and you had to write down what the word was. That was a project done by Google to digitize books, right? Because OCR, a sub area of computer vision, optical character recognition, I give you a picture of something handwritten or a picture of an old textbook, and you need to extract the text for me. That was a task that used to be really hard. Or the newer CAPTCHAs where you need to click on all the boxes with fire hydrant. And they use that for generating data of bounding boxes, segmenting out where in the image the fire hydrant is. So there's a few sort of main tasks in computer vision. There's classification. Given an image, tell me if it's a dog, a cat, or a couch. There's detection. Given an image, draw boxes around all the objects and tell me what they are. There's segmentation. Given an image, tell me for each pixel which object it corresponds to. There's generation. Generate an image for me, whether that's from a piece of text, a conversation, or a class. There's denoising. Given an image that might have like some sensor noise. This is earlier sort of computer vision that really popped up in the 2000s with cell phones. I might take an image, it's grainy. Can you make it less grainy? Can you up the resolution? Panoramas used to be like that feature on your iPhone where you sort of start taking a picture and you drag it around the room, and now you get this panoramic image. That used to be a really hard task in computer vision. How do I stitch those different images together in order to produce a panorama? So, and I think that comes back to the artificial intelligence thing, which is like image panoramas, back when that was a hard task, and I forget the decade, used to be artificial intelligence. But now we don't call it artificial intelligence anymore. We call it just, I can take panoramas on my iPhone. Yeah. How is that as a definition descriptor?
That's great. That's a great way to describe computer vision. Next, we'll do natural language processing. It's been a hot topic for 9 months since ChatGPT was released to the public in November of 2022. What do people mean exactly when they say natural language processing?
Yeah, so it's the same sort of thing. Just as computer vision is, AI within this subset modality of stuff that's visual, natural language processing is AI, but within this subset that is text. So understanding documents, generating questions from documents, answering questions like where is the Eiffel Tower located, being able to hold a conversation, right? These are all sort of different subtasks. And NLP has evolved, I think, similarly to computer vision in a way in that it used to be very, very highly structured. Given a sentence, I'm going to tag all the words in that sentence with whether they're a noun or a verb or an adverb, this sort of part of speech tagging, or building parse trees on sentences, which depending on when you went to school, you might remember sort of drawing those trees over sentences. And now it's become completely neuralized. It's just what is the inputs, outputs, what's the data set, what's your sort of loss function.
What do you mean by the sentence trees?
A big part of NLP sort of came out of linguistics and computational linguistics, right? And there was very much this thought that we need this structure in order to actually understand a sentence. But you had a similar evolution in NLP as you did in computer vision. So way back when, very highly structured, lots of what we call feature engineering. So you might, make a list of words that usually reflect positive sentiment, or bigrams, one word and then the next word that usually reflect positive sentiment. And then these fields became more statistical when we had more compute power and we had more data. So I'm going to train an SVM, or I'm going to train a 4-gram n-gram model to predict the next word given all the words so far. And then in 2012, both of those fields sort of became neuralized, which is, okay, we're not really going to use these parse trees, these sort of as part of the pipeline anymore. A better example might be in computer vision. Like, let's say you wanted to classify an image. Is it a dog or is it a cat? So the very first step would be to take the image and to run a piece of the pipeline that would find all the edges in the image, right? And then you would have another piece of the pipeline right above that statistically would say like Hogg, histogram of gradients. Given that there are these 3 edges in this position, sort of here's what I think this class is. And I'm sure I'm butchering some stuff because I studied sort of pipeline-based computer vision models a long time ago. And nowadays we just train a neural network. So we just put the image in at the bottom of the network. And then at the very top, we ask it to predict, is it a dog or a cat? And what we find is that if you have enough data and you have enough compute and your algorithms are working, you've got a good model, the neural network itself seems to learn these stages in a soft way throughout the network. So if you look at the lowest levels of like a classification network for classifying images, you'll see that there are certain neurons that respond to edges oriented in a certain way, 180 degrees, 90 degrees, 75 degrees. A certain level up, they'll be looking at different parts like noses or feet or paws or tires. And then a certain level above that, neurons will be looking for concepts like a human face or a grass field. So the evolution of both these fields has really been, okay, we used to define all these stages by hand that couldn't really interact with each other or be trained together. And now we just replace it with a giant neural network that's trained end-to-end because that tends to perform better.
With all that out of the way, let's talk about you as an entrepreneur. You mentioned earlier, you had this kind of eagerness to create products, deliver products, work in startups. When did you decide to take the leap from academia to business, and why'd you do it?
So it was the last year of grad school. And the question was, what am I going to do next, right? I've been in school for the past 9 years. And, this kind of maybe goes back to the ideas that led to the founding of Daimon, which I can talk about. But we were sort of in this position, me and my co-founders, looking at all the progress in AI, looking at the work and the research that we had done, and realizing that now was the right time to start where you could actually start building these sort of sci-fi products with the tech that was out there. Like it was starting to mature and it was starting to really take off. And that was the main impetus. And I think that was combined with COVID. There was a sort of 2-year period when we were all locked inside and very lonely. And, we could see the impact that that had on ourselves and on others, and sort of realized that, loneliness, mental health is a big worldwide problem for a lot of people. And could we do something to help them and to make that better? It also sort of piggybacked on an idea that I'd had since I was a kid. I don't think I told you this, but I grew up in Seattle, and I managed somehow as a child to be allergic to literally every animal you can think of. My mom has this adorable story. I think I'm 8 or 9 in the story. When you go to the allergy doctor and they prick you on your arm, like those 12 pricks in a row to see if you're allergic or not? So apparently they had tested all the common animals, and I had these welts on my skin, and I was crying, and I said, can they test more on the other arm? Because I really want a pet. And I turned out to get a fish because I was not allergic to fish. And then eventually a hamster, because I was only mildly allergic to hamsters, right? But, it's fine now. I've got a dog and a cat. I take allergy meds. But at the time, I would read sci-fi, and I would think to myself, as a naive 8-year-old does, you know what the solution is? Clearly the solution here is just to build a robot pet that I can talk to, that I can go explore the woods with. And that's an idea that sort of kept popping up in my head throughout, my journey in AI research over the past 9 years. And I think that kind of came together with, this sense of loneliness, mental health being a problem, like I said, during COVID, and looking at the tech and realizing, wait, this is something we can actually start to build now. So we formally incorporated the company in 2022, and then ChatGPT came out 9 months later. So that was sort of the timing on that.
Yeah, that makes sense. And now, the name Daimon Labs and the reference to his dark materials makes more sense. Talk about why the time is right now for creating robot dogs or machines that can understand emotion. What is this idea of emotional AI, and how do we achieve it?
Unfortunately, the time is not right for robot dogs. We looked into that, and battery density is just not there. So unless you want to play with your dog for 15 minutes a day, it doesn't really work. But on the digital side, there's a lot we can do. And the reason is sort of threefold. One is Moore's law, right? That has sort of really driven software and tech over the past 50 years. And it used to be that every 2 years, your chip would get twice as fast. And then in the early 2000s, that stopped being true. The fastest chip you can get nowadays is 4 gigahertz. And back then it was 3.5. So that completely hit a wall of single core performance. But what kept going was parallel performance, GPUs. So instead of having a single core, we've got 1,000 cores that are each dumb, but they can work on these things in parallel. So parallel computing performance has continued to sort of stay exponential. That'd be one. And it turns out that neural networks are parallel. And so parallel computers are sort of perfect for this. The second is data. The amount of data that's generated on the internet every day sort of got to the point where now we have enough data that we can train models with self-supervised objectives on these data, and they will learn good representations not only of the text, but of the world. And then the third thing is that we finally had algorithms and models that were able to really exploit those two factors. For example, the state of the art in natural language processing pre-transformers was LSTMs, RNNs, and the big difference between LSTMs and transformers is that an LSTM or an RNN has a state, and it reads words one by one. So it'll read a word, and then it'll update its state, and then it'll read a new word, and then it'll update its state again. But that means that when you train it, it's serial over the words. Whereas a transformer, you can train it looking at all the words at once. And so that just works way, way, way better on GPUs and these sort of parallel computers. And that allows us to scale them to be really, really big in terms of model size, but also in terms of the amount of data that they're processing. So I would say those are sort of the three factors.
Why do we need emotional AI? You kind of mentioned your background, but yeah, can we reiterate? Like, why is this something we need?
Yeah, and I think I missed part of your previous question of what is emotional AI exactly, and how do we achieve it? So when I talk about emotional AI, what I like to say is that it's really about two directions, right? It's about, on one hand, the machine understanding you emotionally, where you are, where you're going, what happened, and why that sort of affects you. But also the other way around, the machine being able to display emotions, potentially, one day have emotions of its own, and having the knowledge of what it can say in order to make you feel a certain way. What could it say to make you feel more confident or more supported or more empowered? And achieving it is hard. That's something, we've been working on for a while, and we made a lot of great progress. And one of the biggest barriers there is just the data, right? Large language models tend not to be very good at this task, not very good at theory of mind either. And part of it is that it's not available on the open web, right? Like, nobody will take the last 3 weeks of text messages with their best friend and put it on Twitter. So it's not in their training set. And so a big part of what we've had to do to make this work is to collect data and sort of have an app that people are using in a closed beta and allows us to collect that data. Why we need it, I think I would say one sort of very pragmatic answer, and then one that's a little bit more aspirational. Pragmatically, there are so many clear use cases where giving these systems emotional intelligence, empathy, make for a better experience. Obviously, say like a therapy bot or emotional support, but even imagining, say, a sales bot, right? Doing sales is about more than just reciting facts and figures. It's also about, connecting with the customer and understanding them and understanding where they are. So that's the pragmatic reason. And then aspirationally, I would say, why shouldn't our computers understand us emotionally? I think for a long time in tech and in Silicon Valley, we've been really, really focused on what can the software that we make do, and not enough on how does the software that we make us feel? And sort of injecting those capabilities and that understanding in tech, I think, will make for better products and better people.
Yeah. Yep. It can be frustrating when you run into technology problems. I think we can all relate to that. All right. So those are some of the reasons why we need it. Let's just go deeper into that. Where is this going to be used?
There's a lot of use cases out there. I think for the sales bot example, you probably wouldn't be opting into, I'm going to give the sales bot all my emotional data. I think it would just be that one day the sales bot will be good at reading your emotions from chatting back and forth. And so it'll know, oh, he's feeling frustrated about this, this, and that, and I need to address that in order to make this sale. I think you're going to see it in a lot of places. There's a big hype cycle right now, a little bit of a gold rush in AI. But where we sort of see it happening first is in friendship, companionship, emotional support, that sort of side of things. So, we have two things that we work on at Daimon Labs. One is the sort of platform for emotional intelligence, for high refresh rate learning, for all these sorts of other things like I can talk about more. And the other one is an app that is built to be an AI friend for users. And it's not a person, it's a sort of new social role, maybe something midway between a pet and a friend um, in our lives. But, people will use it and chat with it to help them journal so that they don't have to deal with a blank page when they want to write about their day. They can just sort of answer some questions, have a conversation, have the bot dig into it with them sort of emotionally. People use it to vent. This is something we were surprised by. A lot of people just want to complain to the bot because there's no repercussions, right? They can completely trust it. There's no judgment, and they can vent anytime they want. As opposed to, maybe their friends who might say, "Hey, stop texting me about this. You've been complaining for every day for the past 3 days." So I think those are the areas where we'll see it first. I think also we'll see it in gaming, in media, in those sorts of entertainment experiences, where that's pretty important as well.
What kind of data are you training these models on?
Yeah, so right now it's purely text. And a big part of that is just, reducing the size of the problem we need to solve first. And a lot of people are very comfortable texting back and forth. So we have a huge pile of data. A big chunk of it is the standard sort of large language model data training sets you'll find, which is a scrape of the internet or a common crawl or open web, or it might be called open text. There are quite a few of these data sets, just sort of generic web pages that have been scraped. We also have some subsets that we collected ourselves: short stories, books, fan fiction, patents, medical papers, regular papers, code, just sort of everything that you can stuff into it. And that's the main sort of pre-training set. And then we also have a bunch of dialogue specific data sets. So these are data sets that, if they're not actually a conversation between two people over time, they do sort of approximate that. So we scraped every single YouTube comment in existence, as well as every single Reddit comment in existence, and then a few 100 million messages from public Discord and Telegram groups. And that's like our pseudo dialogue data set. And then now we've got our user dialogue data set, which is the app private beta that we have out, just the entire set of conversations that users have had with the bot. And that one gets a lot more labeling on our end, whether we're sort of manually going through conversations and saying, this was a good response, this was a bad response, or whether that's sort of synthetically labeled.
What are the limiting factors for current approaches for building these large language models?
There's a few. So on a pure technical level, the biggest one is just data, right? So language models are really good at writing a to-do list for you, or an email, or helping you edit something. And that's because, or writing a very simple, React to-do list web app, giving you the code from what your description. And the reason is because the internet is completely chock full of email examples, to-do list examples, et cetera, right? But like I said, nobody will take a deep emotional conversation and post it on Twitter. So that's the biggest technical challenge, is the data. I think the second biggest technical challenge is, what does the model look like for this kind of task? Is it enough to just train a giant transformer on this data like they do for more sort of task-based LLMs? The answer is, in our experience, it doesn't actually tend to be the best way. How do you model this inside the neural network so that it's explicitly got a representation of, through the conversation, what is the user's current emotional state? Based on what I say, how is it going to affect that? And then I think the third challenge, and this is less technical than it is more so societal, the culture in AI, especially since the early 2000s, has been very much empirical, based on benchmarks. The community will collect a data set like ImageNet, and there's a train set you can train on, and there's a test set you can test on, and you run your system on that data, and you say, I got 95% accuracy, and that's 5% better than the last state-of-the-art result, which got 90%. So what we did was great, and you should accept our paper, and maybe you should use the system. And you see that today as well with large language models, with like human eval, big bench, a lot of these sort of question answer or factual tasks, knowing that the Eiffel Tower is in Paris. There's a whole battery of benchmarks and public leaderboards for these systems to know sort of how intelligent are they. But almost none of the subtasks or data sets in those benchmarks are focused on emotional intelligence. They're all very fact-based. They're all very task-based. There's only a few sort of public data sets out there, things like EmoDial or others. The names are escaping me. But until you have that, it's not really something that the research community or the hacker community will focus on and improve. So I think that's a pretty big barrier as well. And I think that's a big reason why it's been relatively understudied compared to, more sort of task-based intelligence. The other thing is that it's harder to quantify upfront. How do you say that a system is more emotionally intelligent than another? And so a big part of the work we've had to do is philosophical debates around that. And how do we quantify it? How do we put numbers to it? How do we benchmark these things? How do we evaluate them?
Right. You said earlier, there's no like measuring stick for intelligence, and I imagine like emotions are like, just like that, or if not more so. So how do you quantify it?
Yeah, in the pure factual, like you could say a component of intelligence is to know things about the world, like remember facts. Great. So now I can build a sub test that asks the model questions like, where's the Eiffel Tower? And we know what the right answer is. It's Paris. Or Las Vegas for the smaller one. Or you could do it for sort of common sense reasoning. Like, why do certain species of rabbits grow white snow in the winter? And the answer is so that they can camouflage and escape predators. Doing that for the emotional side of things is quite a bit harder.
Talk about your technological approach. You've trained this state-of-the-art neural model on, I believe, over 1 trillion data points to deliver artificial intelligence that has memory as well as human-like empathy and the ability to tailor conversations. It seems really difficult to train a model on over 1 trillion data points. I know earlier you mentioned when we were talking about parallel processing that maybe, training on a humongous data set like that is like possible today where it wasn't maybe a couple years ago. But just talk about that approach and how it's working.
Yeah, so the first and biggest thing we had to solve was training efficiency. So we cannot afford the compute to train a super large language model, 180 billion parameters. So we had to figure out, okay, how do we train a little language model to the same level of performance for a much reduced cost? And part of that is just having a stable of tricks and grabbing, the latest tricks out there, things like flash attention for reducing the memory cost of computing attention from n squared to O of n, right? Or alibi, or all sorts of other innovations that you can read about in papers or blog posts. And then on top of that, we have our own modeling innovations, and that really comes from understanding the trade-offs. So one big trade-off we had to make is that we're not trying to build a natural language computer like OpenAI's GPT or Anthropic's Claude. We're building something that is specifically designed for emotional dialogue. And because it's specifically designed for emotional dialogue, we can make trade-offs. So one big one is that our model is completely architected around retrieval, not the sort of basic, chat with your PDF style retrieval, but doing retrieval over the entire data set, all trillions of those tokens as the model is reading and writing. So it needs super low latency constraints, and that becomes a whole engineering problem. But if you do it in that way, that gives you a 25x boost, and you can train a model for 25x cheaper. So all of those sort of tricks came together to allow us to train our little language model. It's got about 8 billion parameters to state-of-the-art comparable, sort of GPT-3, ChatGPT level performance on dialogue, but 100 times cheaper. So we only had to spend $30,000 in cloud compute to train it. So that's one big piece. I think the other big piece, and this is thinking about things like memory or personalization or really understanding empathy, is to try and look at the system in a different way. And the analogy I really like here is systems neuroscience. So if I can go on a tangent for a second, the human brain has many different areas that are doing different things and communicating with each other. And in contrast, the AI systems people are building today are monolithic, one giant model. And so the question is, why is that? And I think one thing that's illuminating is looking at comparative systems neuroscience. So how is the brain of a human organized? How is the brain of a cat or a dog organized? And when you look at cats, they're basically two things smushed together. Cats have really good understanding of visual space, geometry, physics, jumping around. They're little master circus escape artists, right? And that's smushed together with a really, really good associative memory, in contrast to episodic memory. So an episodic memory is to say, 3 weeks ago, I know that I ate eggs for breakfast, or I remember the day when I got accepted into college, right? It's memory of an episode in your life. Associative memory is the ability to associate. You hear a sound and that's connected to something in your head. It's a little bit more Pavlovian. So cats are like a very, very good associative memory stuck together with, all these sorts of understanding of physics and hunting and all these other things. But humans are not just a giant associative memory. We also have episodic memory, right? We also have planning and a workspace and all these sort of other features. And when you step back a little bit and you look at the language models of today, I think it becomes pretty clear that we shouldn't ask them to do everything. What is a language model doing, and how does it function as a component within a broader system? So I said associative memory. It's a very old idea. If you think about BERT, that's an example of an auto-associative memory, right? We're training a transformer to, given a sentence with some words masked out, fill in the masked words. It's just definitionally an associative memory. And GPT is as well. It's a little bit more heteroassociative because you're asking it to predict the next word given all the words so far. And so when you frame it that way, it becomes pretty clear that the language model adds a lot, but it needs to be a component in a broader system. So what we've done technically is to bring back a lot of maybe older ideas from AI, cybernetics, neuroscience, and kind of take that systems approach. So giving our agents the ability to have an episodic memory through, embedding, retrieval, chunking, having a sort of stateful workspace. Like, what are the 7 things that are in my head right now that I might pay attention to or use to respond to you or to take an action? And having that be dynamic, where the system is constantly updating that, adding entries, removing entries, editing those items, and only really using the language model for parts of that system and for certain kinds of decisions that are made in that system, if that makes sense.
Can you talk about your principles at Daimon Labs and why those are important to you?
Yeah, absolutely. So the first big one is data privacy. And, I think everyone has a right to privacy. I feel like that kind of goes without saying. And a big part of that is there's a high level of user trust. For example, when they're interacting with our app, they're talking about deepest, darkest secrets, what happened today, all sorts of really deeply personal information. And so it's important that 1, that data is secure. 2, we don't sell it to other people or use it to sell ads. And 3, that if they want to delete their data, they have the option. They can just press a button and it's gone from our servers. The second big principle we have is really focusing on empowerment, not engagement. And when you look over the past, 10, 15 years, I think I said this earlier, we've been very focused in tech about what software can do, not about how it makes us feel. when you look at social media and a lot of these sort of ad driven business models, their incentive is to have you scroll on the app for 24 hours a day. And it doesn't sort of matter how that makes you feel. It just matters that you do that and you keep coming back. But I remember when I was a kid, the Nintendo Wii came out and I would play that thing for hours. It was fantastic. And if you played it for too long, it would pause the game and it would flash up this screen with, a sun in the blue sky, a green field, a tree, a river, and it would basically say, go outside. Like, you shouldn't be staring at this thing for 2 or 3 hours, or however long you've been doing it. And that makes it clear that it's really a design decision, because the Xbox and the PlayStation never did that. It's really, what is your goal when building the product? So our goal is not to maximize engagement or the time spent on it. In fact, that costs us more money because running these models is pretty expensive. You need to run them on pretty pricey GPUs. It's really to maximize what people get out of our product and how it makes them feel. And then the third one is respect and empathy, which is just that, all these systems that we build, whether it's on sort of the platform side or the bots, the beans in the app side, they should have respect and empathy for all users, right? No matter who they are, where they come from, what their beliefs are.
Well said. Before we get out of here, what is the best way for our listeners to reach you and Daimon Labs?
Yeah, so my email is Ryan, Ryan, at daimon.chat. That's DAIMON.chat. And if people want to try out the beta, then they should just sign up on the waitlist on our website.
Awesome. There's our little call to action. We're going to end the show there. If you liked this episode, why not subscribe wherever you get podcasts and leave us a rating? Thank you all for listening. And thank you, Ryan, for joining the show today.
Absolutely. I had a great time.